Today we are going to talk about the topic oscillation. Let us go into the video. Oscillations. The physics behind this oscillation help us to understand what is called as wave motion. So we are familiarized with various types of motion. Among them, a special type of motion which is called periodic motion. A motion that repeats at regular interval of time, that is what is called as periodic motion. So a type of periodic motion which happens to be around a mean position, that is, the motion to and fro about a mean position is what is called as oscillatory motion. So the a special type of oscillatory motion in which this acceleration of a particle executing is directly proportional to the displacement made by the particle, then the motion is called as simple harmonic motion. Simple harmonic motion is a special type of this oscillatory motion. So as to represent the simple harmonic motion, we have an equation for us to represent the simple harmonic motion, which is given by y equal to a into sine omega t. So in order to find out this velocity of the particle executing the simple harmonic motion, we need to differentiate this with respect to time. Therefore, we know this velocity is given by dy by dt. On being differentiate this, what we obtained is v equal to a into omega into cos omega t. Here we can understand this a omega is what is called as the maximum velocity of the particle executing simple harmonic motion, and omega t is the phase of the particle that executing simple harmonic motion. Then we can change this expression for this velocity in another form, that is v equal to a into omega into root of 1 minus sine square omega t. As a result, after being substituted, what we get is v equal to omega into root of a square minus y square. So this formula is a familiar formula as to solve problems. We have found the velocity of a particle executing simple harmonic motion is given by v equal to a into omega into cos omega t. So for the same particle executing simple harmonic motion, we can find out the acceleration. Acceleration of a particle is given by, that is what is called dv by dt. Therefore, after being differentiated this velocity v equal to a omega cos omega t, what we get is a equal to minus a into omega square into sine omega t. So this is nothing but this displacement of a particle executing simple harmonic motion. Therefore, the acceleration is given by a equal to minus omega square into y. So this is an equation. This is what is called as a differential equation that governs a simple harmonic motion. Since we are bothering about this periodic motion, as to represent this periodic motion, we have some periodic functions. These periodic functions generally to be sine omega t, cos omega t, as well as the combination of these functions that represent this simple harmonic motion. As to check whether an equation is simple harmonic or not, what we have to do is we have to make a differentiation of twice, and we have to get the expression as a equal to minus omega square y. So if it is a equal to minus omega square y, then we can identify the given equation as a simple harmonic motion. As a matter of example, let me give an example. Y equal to a into sine omega t plus b into cos omega t. So this is an equation. I need to check whether it represents simple harmonic motion or not. For that, let me differentiate this with respect to time. So dy by dt equal to a into omega into cos omega t minus b into omega into sin omega t. So in order to find out this acceleration, I have to differentiate again. So what I get is a equal to dv by dt. So as a result, the equation becomes a into omega square sin omega t minus b into omega square cos omega t. So after taking this minus sign outside this, I can have this a equal to minus omega square into y. So from this I can understand the given equation is simple harmonic motion because it represents it a equal to minus omega square y. So another example, we can make use of it. Y equal to a into exponential of I into omega t. So you can differentiate this twice and you can identify this a equal to minus omega square y. Therefore this equation also represents this simple harmonic motion. So let me have a potential energy function. U equal to 4 into 1 minus cos 2x. So I am going to show whether it particle executing simple harmonic motion or not. So what is given as potential energy is given. So I have to find out this acceleration of the particle executing simple harmonic motion. So there is a relation connecting the force acting on a particle to the potential energy by the equation F equal to du by dx. We can make it to be a positive quantity because the force is opposite to the change of this potential. The on being differentiated, what I get is F equal to minus 8 into sin 2x. So this is an expression for force acting on the particle that executing simple harmonic motion. From this I can find out the acceleration of the particle executing simple harmonic motion. So let me assume that the oscillation is small oscillation, sin 2x becomes 2x. For small oscillations, this F can be written, the force can be written as minus 8 into 2x. So the acceleration, suppose the mass of the particle is given as 1 kilogram. M equal to 1 kilogram, what I get is A equal to minus 16 omega x. So let me have this. So definitely this is an equation that represents the simple harmonic motion. So we can equate this with the general equation for simple harmonic motion A equal to minus omega square x. Therefore I can identify omega square as 16 and omega as 4, 2 pi by t equal to 4, therefore t equal to pi by 2. So this is the way we need to find out the period of oscillation associated with the particle that executes simple harmonic motion. So let us find this energy of a particle executing simple harmonic motion. So the total energy of a particle executing simple harmonic motion is a summation of the potential energy as well as the kinetic energy. So the potential energy of a particle executing simple harmonic motion is given by U equal to half into m omega square into y. So the energy of a particle executing simple harmonic motion is a summation of potential energy of the particle as well as the kinetic energy of the particle. The potential energy of the particle is given by U equal to half into m omega square y square, while the kinetic energy of the particle is given by half into m into omega square a square minus omega square. So the total energy of the particle is a summation of potential energy as well as the kinetic energy. As a result, what we get is half into m into omega square into a square. So this is an expression for the total energy of a particle that execute simple harmonic motion. Now I can find out this average potential energy as well as the average kinetic energy over one complete period of oscillation. So since it's of a statistical average, I have to find out this variation of this potential energy over one complete period. So the equation is 0 to t So the statistical average of the potential energy is given by integral of 0 to t u dt divided by integral of 0 to t dt. So on being substituted, this equation becomes average energy u equal to integral of 0 to t. In the place of u, we can place half into m into omega square y square into dt, integral of 0 to t dt. So since y is a function of time, I can represent this half into, so integral of 0 to t dt, that is 1 by t. Now an half is there, half into m into omega square, integral of 0 to t. In the place of this y, I can substitute a square sine square omega t into dt. So after taking this a square outside, integral of 0 to t sine square omega t, we know that it is of 1 by 2. So 1 by t half into m omega square a square into 1 by 2. So this is the average potential energy of a particle executing simple harmonic motion. Similarly, we can find out the average kinetic energy of the particle executing simple harmonic motion. The average kinetic energy, that is equal to integral of 0 to t half into m into omega square a square minus y square into dt divided by integral of 0 to t dt. Therefore, the average kinetic energy is given by 1 by t 1 by 2 m omega square integral of 0 to t a square minus a square sine square omega t into dt. As I take this a square outside, what I get is 1 by t half into m omega square a square. Now what I have is 1 minus sine square omega t. So on being this, it transforms into cos square omega t into dt. So again, the integral of this 0 cos square omega t over the period 0 to t gives you off. So I will end up with the same result as that of the average of the kinetic energy, potential energy. So this average of this kinetic energy and average of the potential energy, that remains the same.